Hello, this is Mahendra Didia. This is the last module in this book, module number 16. It focuses on emulsion quality and clinical study formulation development. In this submodule, we build on knowledge based on quality of products previously covered in modules 8.1 and 12.1. Reader is also requested to refer to module 2.3 for additional information on quality by design. Reader is also requested to refer to module 15.2 on manufacturing and composition of ruxolitinib phosphate. This slide is a refresher slide. We have discussed this in previous modules. Let's look at what is quality of product. Quality of product comprises of three components: QBD, quality by design, quality control testing, and ongoing stability studies. The QBD must be built during the formulation development. It is done through identifying CQA, critical quality attributes, and related critical material attributes, CMA, and critical process parameters during production, packaging, and storage. Readers are requested to review module 2.3 for additional information. Let's look at QBD for drug, tapinarof 1% cream. I've given you formulation here. This formulation does not necessarily come from FDA documents, as FDA documents do not identify exact composition. The active drug is 1%. Oil phase is shown here. EDTA, complexing agent, emulsifiers, DMSO, transcutol used in enhancing permeation. Carbomers and carbopol polymers are used. Increased viscosity, purified water, benzoic acid as a preservative, BHT as an antioxidant, citric acid and sodium citrates as a buffering agent, and sodium hydroxide pellet for pH adjustment. The process is shown here. Water is mixed with benzoic acid, EDTA, and water-soluble ingredients such as citric acid and sodium citrate, and pH is adjusted to 6.0 with sodium hydroxide. Oil phase consists of mineral oil, castor oil, span, which is sorbitol oleate, and BHTs are added. Carbopol 981 is added to the oil phase and it's mixed until it's homogeneous. Emulsification, oil phase is slowly added to the water phase and high shear homogenizer are used. Active phase, the active drug is dissolved in polyethylene glycol and transcutol. Drug is then added slowly into the emulsion and homogenized. This procedure here is written in a laboratory mode. Let's look at QBD. CQA risk for the drug. The initial CQA risks are identified. CPP and CMA are not from the FDA document. I've added CMA and CPP for ease of understanding. Medium and high risk needs to be mitigated. Medium risk are defined as tube content uniformity. That would be process related. Globule size distribution, that would be process related. Crystallization of a drug. Drug is dissolved in transcutol, polyethylene glycol, and therefore there is a potential for drug to crystallize. That was identified as a medium risk. Drug-related degradation, and that needs to be mitigated. In vitro release. If drug crystallizes and precipitates, then it will not completely release. And that's identified as microbial controls are generally initially identified as a medium risk since product is not sterile. Extractable, leachable from the container closure system are identified as a medium risk Since product contains surfactant, drug manufacturer provided information that mitigated all these risks too low. For in vitro drug release, conduct in vitro IVRT clinical correlation study. Based on that, in vitro release test specifications were provided and were accepted by FDA for the drug. FDA does not provide details of release specification, and this is redacted as it apparatus is French cell system, a diffusion cell system. Stir rate for French diffusion cell is 600 RPM. Receptor contains a solvent system shown here. Membrane is a nylon 0.45 micron pore size and 25 millimeter diameter. Reader is requested to review 13.4 module for in vitro release. Drug release for cream is shown in a different document. Again, I want to point out this is not an FDA specific agent or FDA related document. It is obtained from a different source. Amount of drug released against square root of time is plotted, and that gives a straight line. Based on that straight line, one can calculate release rate, and I've calculated that as 41.64 microgram per cm square per square root of minute. Not this particular information, but this type of information will be provided for multiple lots throughout stability, and based on that, release specification as well as end of the shelf life specification will be provided. Let's look at quality by design for ruxolitinib phosphate oil and water emulsion. Reader is requested to refer to module 15.2 for the composition and process. Critical quality attributes here is uniformity in container. And this is related to the uniformity of bulk product. In this case, drug is dissolved in aqueous phase and then emulsion is prepared. This was identified as a medium risk. Drug product specifications were provided and uniformity of the drug in container was acceptable as a flag and the risk was lower. Let's look at this quality of product, quality control specification. We have reviewed quality control specifications for other products in previous modules, and I will not go into details of. We'll look at the emulsion portion of the quality control test specifications. And we'll also look at importance of viscosity. There are several methods to identify type of emulsions. One has to be careful in using these methods as emulsion can break and separate and will give false results. In addition to that, we need to look at stability of emulsion. Let's look at the video. Emulsion quality control test. In this case, specifically, we are interested in type of emulsions. And we have looked at these type of emulsions in previous slides: oil in water, water in oil, microemulsions, multiple emulsions. The test methods generally are used: dilution test, dye test, filter test, fluorescence, and conductivity test. These tests have limitations. The stability testing, aging, temperature is very common. Centrifugation to speed up, humidity, light, agitation, and phase separation is very important. Viscosity is critical. Zeta potential, particle size, and instability of suspension. We will look at some of these properties. Let's look at viscosity as a criteria. In this case, two products are compared. They both appear same from touching, stirring, shaking perspective. The manufacturer is the same. One has a coconut and other has a different flavors. Let's look at the video to see how viscosity can help differentiate the product. So two products are coconut and orchid flavor. Viscosity profile is generated to see the difference. So here's the profile of the first product, And we can understand the shear rate and shear stress relationship. And these are both shear thinning products. Let's look at the viscosity profile of the second product. And flow curve again shows shear thinning effect. Now we can compare these two products, the effect. In this case, viscosity of orchid product is about 10% higher at different shear rates as compared to the coconut product. This type of information is helpful in understanding stability profiles and the quality of the products. Let's look at the mechanism of degradation of emulsions. As part of quality control stability, we need to look at how emulsions break down. So this is the emulsion. It can coalesce. These particles can collide and grow. Particles can flocculate together. If the particles are heavy, they can sediment. If particles are oil, generally they will cream, they'll float on the top. In addition to that, particles can grow at the expense of the other particles, such as oswald ripening, where particles are growing at the expense of the smaller ones. In photomicrograph here, we can see that 4 days at room temperature, you can see uniformly distributed particle size. At 1 month at room temperature, there's not much change. However, at 1 month, 45 degrees, we can see particle coalescence into a larger particle, and eventually this will then separate into oil and water phases. Let's look at double emulsion. It is an emulsion of an emulsion. Primary emulsion, not stable. Here is double emulsion. Primary emulsion is shown here, and this is water. Oil is yellow and water as an example. And the multiple globules are present in double emulsion. Internal water can coalesce, as shown here. Internal water flocculate within the primary emulsion. The water droplets can be expelled, go into the outer water layer. Water can diffuse out selectively, so the globules will become smaller. Water can diffuse in, and globules can become bigger. So double emulsion have multiple pathways of instability. For drug release, drug can release prematurely if it's very close to the surface of, as shown here. This is stable. Water can exist. Drug is not released. That may be acceptable or may not be acceptable depending on the final outcome. Let's look at stability data on ruxolitinib phosphate in oil and water emulsion. Reader is again requested to refer to module 15.2 where composition and processes are presented. This is typical of the data submitted to FDA. I like to point out that FDA documents may not include detailed stability information. Accelerated conditions are 40 plus or minus 2 degrees centigrade and 75% plus or minus 5% relative humidity. Studies are conducted for 1, 3, and 6 months. Room temperature or storage temperature is generally 25 plus or minus 2 degrees and 60% relative humidity. Studies are conducted at initial 1, 3, 6, 9, 12, 18, 24 months and annually thereafter. The test parameters are appearance, physical parameters, pH, weight loss, and viscosity, active ingredients, parameters, API assay, related substances and total related substances, and microbial tests. Overall data shows excellent stability. There's a slight change in viscosity at 6 months, accelerated condition. Looking at room temperature data, there is not significant changes in viscosity. And product shows excellent stability from assay perspective, degradation perspective, pH, and there's no weight loss recorded. The product has 2-year shelf life at the room temperature storage conditions. Let's look at research formulation and stability. Stability is conducted on nanoemulsions, and we know that nanoemulsions are generally more stable compared to the macroemulsions of the same formulation. Rice bran oil, sorbitol oleate, and PG30 castor oil are used as a surfactant. Purified water is used as an aqueous media. The composition is shown here. Oil is kept at 10%, except in one experiment. Concentration of the surfactant is changed. Amount of water is adjusted to make sure the composition is 100%. The process here used is a laboratory process or a research process and uses phase inversion technique in which water and oil emulsion is made, water is added, it goes through a transition phase of oil, water, and oil emulsion through laminar phase, and eventually to a nanoemulsion through phase transition. Phase diagram shows that in this region here, nanoemulsion is formed, region 1. All other regions are not nanoemulsions. Stability was conducted using 10-10-80 formulation with a droplet size of 69 nanometer. The protocol is 25 degrees, 40 degrees, and 5 degrees, up to 90 days. Tests were droplet size, pH value, and electrical conductivity. The results are shown here for the nanoemulsion 10-10-80 formulation. The particle size distribution shows the growth of particle, and it points to oswald ripening at 40 degrees at 90 days. Electrical conductivity tests will show the separation of oil and water. It's very stable at 25 degrees and 5 degrees for 90 days. Conductivity is increasing slowly at 40 degrees, and at 90 days, oil creaming is observed. pH values are stable at 25 and 5 degrees. They decline at 40 degrees, and at 90 days, emulsion separation is shown. So these type of studies provide mechanistic understanding of the emulsion, its stability,